Hi, so before we get to nitrogen nucleophiles, which will be kind of the last thing we talk about with carbonyl additions, before we get to nitrogen nucleophiles, I wanted to quickly talk about just a little bit more on reductions and oxidation. So lithium aluminum hydride and sodium borohydride were two examples that we talked about in the previous slides, and then I wanted to come back and circle back to organic one and do some of the oxidation stuff. So things like PCC, chromic acid, just a quick review of kind of what those things look like. So this is going to be about alcohols and carbonyls and how we convert between the two. So it should be a pretty quick lecture, but it's going to be mostly a list of reactions and kind of what does what. So good for your notes, and we'll see how it goes. All right. So really quickly, we have two types of reactions. We have reductions and oxidations. And so to define these terms, in oxidations, we make more CO bonds or less CH bonds. So to oxidize a carbon, either we're losing hydrogens from carbon atoms or we're adding more bonds to oxygen. Reductions are, of course, the opposite of this. Reductions make more CH bonds or less CO bonds, or both. Many of these things will do both. Right, so we had talked about lithium aluminum hydride and sodium borohydride. So if we have an aldehyde, and I'm just going to choose any garden variety aldehyde, right? This aldehyde has two bonds to oxygen. This carbon has two bonds to oxygen, and it has one bond to hydrogen. If we treat it with sodium borohydride, we know that this is just H minus, and we know how this is going to react. H minus is going to come in, it's going to add to the carbonyl carbon. We're going to break the carbon-oxygen pi bond, and we're going to push the electrons up toward that oxygen and make a new lone pair. And so we end up with a negative oxygen up here, and we end up with two hydrogens now attached to this carbon. So notice, of course, that we've gone from having one CH bond in the beginning to having two CH bonds as our product. We have two CO bonds in our starting material. We have one CO bond in our product. So this is clearly a reduction, right? This is a reduction. And then we would work this up, right? We would add some kind of H plus, some mild acid that would convert this to the alcohol. So notice that as we go from carbonyl to alcohol, right? So we have an aldehyde over here, and we have an alcohol as our product. This is a reduction. Same thing with lithium aluminum hydride. It will do the same thing. If you have a ketone instead of an aldehyde, you're going to get the same thing, right? So reductions in general do this. The opposite reaction is, of course, an oxidation, and we talked about those in Organic 1 briefly at the very end of the class. Right? So if you use pyridinium chlorochromate, or PCC, you get an oxidation reaction. And we don't need to know the mechanism of this, we just need to know how this works. Right? And notice, of course, that we're going from having one CO bond to having now two CO bonds. So we're making more CO bonds. We go from having two hydrogens at this position to now having only one. And so this is clearly an oxidation. And notice that, of course, this is going the opposite direction. In reductions, we went from carbonyls to alcohols. In oxidation, we're starting with an alcohol and oxidizing to create a carbonyl. So that's a pretty rough definition of reductions and oxidations. I think that there are you can definitely go into more detail if you want. There are certainly other ways to do reductions and oxidations. So this is by no means an exhaustive list of how oxidations and reductions go. We've actually seen other reactions that are reductions, but we haven't named them as such. So there's a lot of oxidation reduction reactions. This is just, when we talk about carbonyls, these are the most important ones. So the last thing that we're going to do is just kind of list off what are the things that all of these reagents do. So we're going to start with, let's say that our starting material is a primary alcohol, right? So if we're going to oxidize it, if we oxidize a primary alcohol with PCC, we get an aldehyde, right? That was the example that I just drew on the previous slide. So we start with primary alcohol, we get an aldehyde. If we use chromic acid, H2CrO4, we get a carboxylic acid because H2CrO4 is kind of the big hammer of oxidations, right? H2CrO4 will keep oxidizing this compound until there are no hydrogens remaining on that carbon. And so when we do that, we go all the way up to a carboxylic acid. So alcohol to carboxylic acid, we can do that using H2CrO4. Secondary alcohol. Right, so we only have one hydrogen here. We get a ketone if we use PCC because we oxidize the alcohol to a carbonyl. And if we use H2CrO4, we actually also get a ketone because what we get is we oxidize that carbon until it doesn't have any hydrogens left. But in this case, that means we only lose one CH bond and gain one CO bond. And so depending on our starting material, sometimes PCC and H2CrO4 will give us the same thing. Other times we'll get very different products. Okay. All right. Let's do reductions. So reductions, we're going to start with a carbonyl. Let's start with an aldehyde. And actually, I'm going to cheat here and throw in another oxidation. You can oxidize an aldehyde if you use H2CrO4 and you can get the carboxylic acid. Okay. Nothing happens here. We don't ever oxidize aldehydes with PCC. It's just not a strong enough oxidizing agent. Right. Okay, so this is here, this is here. Over here, we're going to put sodium borohydride, NaBH4, and lithium aluminum hydride, LiAlH4. Right. So these don't do anything to alcohols, right? We don't use these to react with alcohols, so this whole quadrant is just a nothing. Okay. Sodium borohydride, if we reduce an aldehyde, this was the example that we just put on the previous slide, you get out a primary alcohol. Right? So just like the opposite of the PCC reaction, if you start with alcohol and oxidize, you get an aldehyde. If you start with an aldehyde and reduce, you get an alcohol, right? Same thing with lithium aluminum hydride. These give the same product when we treat an aldehyde. Okay? All right, ketones. Nothing happens here, nothing happens here. If we reduce a ketone, we're going to get a secondary alcohol. Same mechanism as the previous slide, right? We add a hydrogen to that carbon, we break the carbon-oxygen pi bond, push the electrons up onto the oxygen. And in both cases, we end up with a secondary alcohol. So far, we have two reactants, sodium borohydride and lithium aluminum hydride, that give us the same product, right? If we reduce an aldehyde or if we reduce a ketone, we get the same thing. The only difference between these two is if we have a carboxylic acid, or actually I'm going to say we're going to be a little bit more general. We're just going to say some carbonyl derivative. Oh, shoot. Right, keep writing the wrong thing. Carboxylic derivative. All right, so what's a carboxylic derivative? It's when there is a heteroatom attached to the carbonyl in this position. So instead of an R group or an H group, we have some kind of oxygen or nitrogen or chloride or bromide or something that's not carbon or hydrogen here. In that case, we don't get any, okay, where's oxidation doesn't do anything, right? Because this is already, there's no hydrogens there. Sodium borohydride doesn't do anything, no reaction. Right? So sodium borohydride would just give you the same thing back out. But what lithium aluminum hydride will do is it will give you a primary alcohol. So just like chromic acid will keep oxidizing something until there are no hydrogens remaining on that carbon, lithium aluminum hydride will keep reducing things until there are no pi bonds remaining, right? And so in this case, I lost my marker again. We keep adding hydrogens to that carbon until all the pi bonds are gone. And so once this CO pi bond is gone, we lose the X group, we end up with a primary alcohol here. So this is the big difference between lithium aluminum hydride and sodium borohydride is once you get away from aldehydes and ketones, they react very differently. Okay, so lithium aluminum hydride and sodium borohydride are the same when we are reacting them with aldehydes or ketones, but if you react them with something that is of a higher oxidation state, has more heteroatoms attached to that carbon, then you get a pretty big difference between them. Sodium borohydride no longer reacts, lithium aluminum hydride does. The reasoning behind that is that aluminum is less electronegative, so it's easier for it to give away H minus, right? And so it is a better reducing agent. It adds H minus in a more efficient way. So that table is a good table to keep in mind. It gives you all your oxidations, all your reductions that you'll need to know for this course.